say only 2 sentences, and then you can. Okay, sit down, please, and we will start. We have, okay, people are coming. So, let's start our second morning session with some insight into dependable service design for 6G visionary use cases by Oliver Hofberger from BNR. Oliver was the leader of the work package 1 in the project, which covered this dependable service design, the use case analysis, and the architecture. So, floor is yours.
Thank you, Janos. Welcome everyone here in the room and also on the screens. My name is Oliver Höfberger. I'm with BNR, and BNR Industrial Automation is basically a customer or maybe a future customer for the technology we are developing at the moment. In that sense, I'm not telling you anything about the deep technical solutions that we want to provide in the future 6G systems, but I want to talk a bit more about the consumer side. We want to consume services, we want to consume dependable services, and this is the focus of the presentation today. I will start basically to introduce the use cases. Otherwise, we could not really talk about the requirements we have from those use cases, what dependability means in the context of those use cases of the services that we expect. After that, I will give an introduction about the flexibilization of the requirements. So typically, requirements are quite strict, but in the type of systems that we are facing, the uncertainty needs to be handled somehow, and in that sense, probably we also need to flexibilize the requirements. After that, I will introduce an interesting concept that we developed or that we designed during the work in the project, which is about the adaptation of the application itself instead of changing the system if the environment provides that need. Good. If we're looking at a typical use case in the future, we're expecting factory automation. Adaptive manufacturing is a use case that specifically is interesting for our company. So automation systems in the factory, we see here a lot of processing stations. We see vehicles moving around, automated guided vehicles, for instance. These are different types of sensors that are mounted in the environment, in the factory. There is a big warehouse in the factory. There is a server room for edge computing. There is backbone communication using TSN. But there is also some new technologies in the future company, like extended reality systems. People are walking around for maintenance reasons, maybe for their work reasons, for the type of production. They wear different devices which need to be connected to the company environment. There is also exoskeletons in such systems which should assist people in heavy load situations to do their work. And if you're looking at such a use case, we see that there is a lot of connectivity needed. All of those parts need to interact closely together in that situation. Another interesting use case, which is slightly different, is also automation, mobile automation in that case, but smart farming. So here we see an image. Don't worry, we did not harm any animals during the project, so this is just AI-generated image. But we see here an automated harvester. This is driving on the field autonomously. There is trucks. They should take the crops from the harvester during its operation. It should also be fully automated, and to protect wildlife, to protect the system against any harm, against any damage. We also see that there will be many drones in such situations. The drones would capture pictures and images, and based on that, it is decided if there is any obstacle in the field or not, and then the harvesting process can adapt its speed to that situation. Good. If we're looking in such use cases, we see many new challenges that come up in the future. One of the biggest challenges, of course, is complexity. So we have seen just a few devices and systems that are participating here, but we can, of course, assume that there is many more devices, systems interacting in the future. The combination of many different applications into that system, the scope can extend heavily, and somehow we need to take that basically by abstraction. We also need to design interfaces such that the different parts of the system, the different applications that we see in such use cases, they can be handled individually. Another big challenge is we have multi-criticality in such systems. Many different applications, some of them are more important than the other ones, as you may assume. So there is safety-critical applications, there is applications that are more important for the business use cases of the user, of the owner of the system. And for that, we need systems that are capable of prioritization of those individual applications. And we need to have a clear segregation. We need to be able to segregate the system such that there is no interference between the less and the more important applications. We see dependability, of course, as a very central point, dependability of services. So if I want to provide services, then of course I also want to rely on the provision of the services. And here often there is a trade-off, as you may know, between resource efficiency and the reliability. For that, we need to adapt the system architecture as we planned and did in this project, and also to provide new ways for the service design. Security and trust is a very, very important topic, specifically in the future. There needs to be a clear ownership. There need to be permissions. Who is able to interact in this farming use case? So a new farmer that is probably assisting, also coming with a combine harvester, how can he integrate into such system? So we need security by design that also need to be considered in the service provision. And one aspect that is somehow new, but we also found that very important in this project, is the societal impact. In the use case of the smart farming, we have seen that the animal protection is maybe not the highest interest of the farmer, but there is a societal interest in the protection of the animals. And we should also reward the societal contributions in such use cases by some means. In the project, we had the consideration of the key societal value indicators, and we also want to integrate such indicators into the service descriptions. Good. If we're talking so much about services, then we also need to think, what is a service? I do not want to mess with the 1,000 definitions of services out there. We just tried to find a very concise, simple one. And we consider services basically as a structured capability that is provided by the system in order to support the consumer of the service. So basically, the consumer wants to get a need solved and supported, and he wants to be a value that is created. And if we are talking about dependable service, this basically means that me as a consumer, I would like to rely on the provision of that service. So I think that should be clear for the audience here. So now the question, what kind of services do we see in the use cases that we have seen before? And the first and probably most important service is the service of the application itself, because the application would not be there if there would not be any value that is generated to some consumer or to some user. Maybe this is not that obvious, but it should also be part of the system design in the future, as we may see later, that also the application service needs a precise description, not only the services that are provided by the system, but also the application that would like to enter the system should specify what kind of service and what kind of value it provides. And of course, we have the 6G infrastructure platform services, and here these services are then provided to the applications that may run on the system. Good, of course, and if I want to provide a dependable application, somehow I need to rely on the dependability of the platform. To some extent, I can cover this in the application design by using multiple different platform services in order to achieve dependability, but without dependable services at the lower level, this is hard to achieve. Good. In our project, we covered several different sub-services that are provided by the 6G system. One of them is, of course, the communication service, which is basically the reliable exchange of data between functional entities. So the term functional entity is coming from OPCUA specification, and here it basically denotes the endpoints of communication. But what we see here that the services are typically described by different measures, by different parameters. There may be some performance measures like bandwidth consumption and cycle times that you want to have for your communication. But there is also a qualitative description for those services, like latency, jitter, availability, reliability, many more. So there is not an extensive list here or in the project, but this can be extended as you wish. Another important service is the computation service that we discussed. This is basically the provision of processing, memory or storage resources to the consumer of the service. This can be qualitative measures or qualitatively distinguished between real-time capabilities, non-real-time workloads. But we also need to consider this computation service in the end-to-end design of the application. So also the computation that I get from the system has an impact on the latency between the different functional entities in my application. There is a time synchronization service, very important for time-aware systems, of course, where we expect a reliable provision of a shared notion of time. There are different possibilities or different notions of time, like wall clock times or global times. There is a working clock time, typically known from TSN, where we want to rely on. And there is also some qualitative measures for the time synchronization, like precision, accuracy, but also holdover time, so how long the system can survive without any synchronization in place. Security service is maybe this may be interesting to see here as a service, but also security in the sense of data integrity, insurance of confidentiality and availability. This is basically something that the system can provide in a way that I want to rely on the secure exchange of data. Later we will see that there is a different notion of security in such systems, which is basically the security of the system functionality itself. Here I really want to emphasize that this is basically the security as a service. How to secure the data that is communicated. Security needs to be considered specifically in the real-time environment, that it doesn't introduce a lot of latency, because it then could prevent good real-time control in the systems, and it should be very resource efficient because security needs to go out to the very small devices in the system, like in the sensors of the factory, for instance. Good. Behind those services, there could be many more. We have heard today maybe such a localization service would be very nice in the mobile automation environment, to have services like precise localization of devices, trucks that are moving around. This could be another service. But now the interesting question, so maybe this was not so much news for you, but the interesting question is how we should deal in an uncertain environment with those services. So the stochastics of the environment, they often counteract the provision of the guaranteed services that we expect in the real-time environment. So many applications compete for the same resources, as you may have seen. So in the bigger extent, maybe the system is almost at a very high load, and still there are more applications that want to compete for the resources that are there. And additionally, the environment may provide conditions that counteract the quality of service that I expect, like interferences, and the mobility of devices could also have some impact here. So now the question is, what should I do as the application if the requested services are not provided anymore? Typically, the applications are designed in a way that they need the services. If I do not get some communication, my data is not updated anymore, I cannot do real-time control of my systems. So what should I do in such situation? So of course I can shut down my application. This is often done, specifically if this is some security, some safety related application. I typically need to shut down, go into a safe state. But this is really expensive, and you do not have any value provision anymore. And sometimes this takes minutes, hours to get out of that state anymore. So you cannot always simply shut down the application. And specifically if this is somehow safety relevant. So that's not a good idea to just say that, oh, my services are not provided anymore, I simply stop working. So it would be much better in such a situation if I could ask the application to lower the application, the service requirements. So not needing so much bandwidth or reducing the cycle times of communication, for instance. In the sense, basically, to have low service or low value that I get from the system, it's much better than having no service or no value that I get from the system. So how can we achieve that? It could be quite simple, but for doing this, we need two different concepts that we introduced in the project. One of them is the modes of operation of an application. And this is a specific configuration or state in which the application operates to achieve the intended performance and reliability objectives. So basically, the application has a defined mode in which it operates, and for this mode, you have a defined configuration, you have different requirements for this mode of operation. So what is this good for in the sense of services? Well, on the one hand, almost every application that is now out there in the system is operating in different discrete steps of operation. So typically you have an initialization, you have an operational phase, sometimes you change the behavior of the application depending on what you're doing, and then you shut down the system. There are so many phases. Actually, this modes of operations is already there. In the case of the harvester, for instance, there is a mode of operation because you have the actual harvesting process, but also the harvester needs to drive to the field. Probably it needs to be maintained and so on. There is so many different situations where you would simply change the behavior of the system, and in that mode, which the system is, you typically have different requirements regarding the services that you need. So why should I always go with the highest level of services, which may be possible in my system, if I'm able to change the requirements and asking the system for less services to be provided for a defined amount of time? These modes of operation, they are clearly controlled by the application or the user. So it's part of the application to switch between the modes, and the user can select some of them deliberately. This is nothing the system forces to the application, but this is something that is part of the application to some extent. And it gives some structure for the application, and it provides ways for adaptation, for adaptability. The other concept that we then introduced is the level of operation. This is maybe more important or interesting here, because the level of operation is now referred to as the distinct hierarchical stages at which the application functions. There are different levels of quality that I may provide as an application, and where I expect different parameters for the services. So, well, sounds quite similar like the modes of operation, but actually it is not. So the level of operation is basically different performance levels for the same mode of operation. So as an application, I prepare to be operated in different levels where I can perform differently, where I can provide different varying value, but it's prepared already by the application to have certain levels. And in each of those levels, I have different requirements regarding the services. This allows then for performance optimization, which is more optimistic than graceful degradation, but typically you would optimize your system as long as possible, and then if there is a problem, you gracefully degrade because you know your system is prepared to operate in a lower quality level as well. But this one, the level of operation is now selected by the system. In case of any interference, the system can select and demand the application to change the level of operation. And this allows for dynamic adaptation and to increase the dependability, the overall dependability of the applications and the systems, as we now will see. So what's happening in such a future deterministic 6G system is that there is somebody who owns the system, of course. The owner of the system configures the system itself. Of course, there is so many configurations, I know, but some new concept here is to configure a value function. The owner of the system decides what type of applications are more valuable, what's more important in that system, that even may go to some governmental rules that may have an impact here on the value function. Like in areas where maybe wildlife protection is more important, we can increase the value of wildlife protection than in areas where this is not the case. There is a clear value function that is defined by the owner of the system. Then there is many different application owners, and everyone wants to have its application running in that system and being connected to some extent. And those application owners need to register at the centralized system, and they provide a list of requirements for the different levels of services they may be operated. Then the centralized deterministic 6G system would calculate the value based on the value function that the system owner defined. The system automatically ranks the application, and it would provide the different resources to the application. After this has been done, it would inform the applications and provide the corresponding services. So every application would receive the service at a certain level it previously defined. And now, if something strange happens, like an interference in the system, resources are low, changes in the system, what would the system do? So we do not want to shut down. We cannot simply kick out any application. But in such a case, what we would do is basically we simply re-trigger the allocation process and doing the same thing again. So calculation of value should be still valid, so this could be incremental. We do the ranking again, and we do the resource allocation, but probably due to prediction, as we have heard and as we may hear later, they could predict that in the next amount of time the system cannot be operated stably, and then we need to change the resource allocations. And the applications are informed in advance, and then the applications are operated at different levels as before. So how could this look like? Again, we do have the harvesting process here with the drone sending the data to the edge system, and the edge does the obstacle detection. And in the first scenario, we see that the wildlife is detected. There is an animal in the field. The safety application triggers a mode switch, which says, oh, let's drive at half the speed. The vehicle slow down. The image rate is increased because we would like to follow the animals, and the bandwidth, there is a bandwidth increase request to the system. This is an intentional switch of the mode based on the application. The other scenario is the opposite. There is an interference in the system, resources go low. The system decides that we can still operate if we lower the resource requirements. If we switch to a lower level of operation in this obstacle detection, the lowering of the level is reported to the application, and the harvesting process again needs to slow down because we have a slower image rate. but we can still provide some reduced application value. Good, I'm almost at the end of my presentation. So to conclude, the future industrial applications, they require dependable services. And to achieve these dependable services, we also make the infrastructure adaptive and also the applications adaptive. In the stochastic environment, I don't believe that we can achieve to handle this completely in the 6G system. So we also need to integrate the applications into this dependable service design. If we have smart definitions of services, this enables the automated optimization of the value of the overall system. So the system can now decide how to optimize the value provision, and we do not always have to tweak around all the parameters to get the best out of the systems, but of a concrete system or installation, the system can do this on its own. We should include the societal value into the value function, because this should also be considered in the future more than it is done nowadays. And finally, of course, with great power, there is also great responsibility. And so we also need to consider security at the very bottom of such systems. So if we can change a lot, if we can ask for adaptation, we of course need to implement the security measures to secure such systems in the future. Thank you very much for listening. If there is any question, then please.
Thank you for a very interesting presentation. So in one of the previous slides where you have the figure that say the system owner and the app owner, so in the case of private 5G, what is the system owner and what is the app owner? Should they be the factory owner, for example? Thank you.
Yes, of course. In such a case, if there is one factory owner with a private network, this person may be the system owner, or is the system owner, or the company itself. But in such cases, the application owner is basically also the same person, probably, or the same heuristic person. But actually, if I'm a maintenance personnel, if I'm a department owner, I'm sometimes competing with other departments within the company. I need to maintain the system. I need to make my team more productive. I'm somehow also competing against resources. If I want to introduce more HEV systems into in my environment, so this is basically an abstract notion of application owner and system owner. It's not so much about having conflicts within a company, and maybe the owner is the same, but they're often in different interests, and the applications to some extent are owned by different persons, even within a company. It's easier to explain, of course, in the mobile use case with the farmers and having multiple stakeholders here, but the same could be applied in the factory environment as well, I would say.
Thank you.
Thanks, Oliver. Good presentation. I agree on your second point. A stochastic environment cannot be handled by the 6G. You are proposing integration of applications, but wouldn't that be against of realizing the 6G as a black box, like a switch or some transparent components? So if we want to build this kind of integrated application with the 5G system to deliver an stochastic sort of environment, wouldn't be a bit of conflicting with the basic idea of having like a seamless communications infrastructure or black box?
I would see it exactly otherwise. So basically, if I consider my system as a black box, I need to deal with so many situations which I cannot control, which I cannot really know in advance. And if I'm an application developer and I do not know the exact system environment and I need to deal with the black boxes, it's easier to specify different ways of using my application, probably, and the system then knows what's within the black box and how the system is composed. And then in the real system, it can adapt accordingly and change the levels of operation according to the real system environment. And if I'm changing one of the black boxes, the system can adapt again, maybe to the better, maybe to make it worse, but it's a graceful degradation then.
So thanks for the presentation. I have a questions on you on the, let's say, application domain. I mean, what you propose here gives, of course, let's say, a level of resilience by being flexible to use the system as it is. But of course, it also means that the application must have some awareness, which means it's not like, I mean, I think there's partly the wish. You use the applications that you already have. You want to have flexibility, so you remove cables and put in wireless, but everything else stays the same. Here you anticipate a certain flexibility also from the application side. And at the same time, I mean, there are changes coming to the applications anyway with the adoptions of cloudifications, which is a big topic and so on. So how large do you see the momentum, I mean, of, I mean, this must go hand in hand. The applications for this design need to be at the same time adapting as the systems provide future capabilities or the 6G wireless system. So how do you see the momentum from the application domain for changes that are coming, maybe from cloud computing, that you can integrate this at the same time?
So, well, actually, at least the automation domain, there is not yet a lot of momentum into flexibility, because this is hard to guarantee. This is hard to certify to some extent. But if you're looking at the use cases, even in those domains, actually they would need it. So the builder of such systems, they are not aware, they do not want to have it, but actually they would need it. And they're asking for so many solutions which are kind of workarounds for exactly that cases where the system could decide in that installation how the system can then adapt, how it can improve itself. So bringing this into such environment, having solutions that are really stable would probably create such a momentum. But unfortunately, it's not yet there. So I personally, from my point of view, I got a lot of good ideas, and I see many relations to the customers we're having and to what customers would need. Having a lot of flexibility, but it needs to be handleable and it needs to be guaranteed. And here the question is how we can guarantee the adaptation in a way that the customers can make use out of it.
We have time for one question. Okay.
Thank you, Oliver. 2 days ago, in the Dependable 6G summer school that we were holding at KTH, we were introduced to the concept of communication faster than light. Have you heard of that?
No.
Neither of us had heard of that too. So communication faster than light is the idea to, on both ends of the application in the distributed system, predict from the state information that you have and the state evolution what most likely is going to be communicated next. And obviously AI would play here a big role, and this is of course a marketing slogan, communication faster than light, or an academic marketing slogan. I would be interested in your, let's say, view on future automation systems. To which extent you would rather believe in 5 to 10 years they are exploiting prediction over, let's say, more unreliable channels versus having more reliable systems underneath where you don't need much AI and prediction on both ends?
Well, I think there is room for both sides a lot. So there is some applications that do not allow any predictions at all, because they need to be precise, they need to be super fast. There is some control loops in real systems of a few microseconds. You cannot achieve prediction, you cannot make use of prediction in such systems. So we should put those aside. But at a very high level in such systems where you combine many different applications, I think prediction will be necessary in the future. There is so many things you cannot control at all, and if you would like to control everything in such system, you get such a huge complexity, and in some cases you need to integrate, I would say, prediction into your control, and then you're doing planning. Here, prediction makes a lot of sense. If it goes down to the real physical control, I think there will be some more time needed until the prediction will really play a role.
Thank you, Oliver, for your nice presentation. And the next topic will be about different techniques in 6G system to minimize packet delay latency. So I would ask you, Marilette, to start the presentation.
Hello, everyone. My name is Marilette de Andrade Jardim. I work in Ericsson, and I'm also the Work Package Leader, Work Package 2, for 6G-centric solutions or enablers. And I'm going to present minimizing packet delay variation in the 6G system. Right, here's the content. I'm going to talk a bit about the application level and their needs. Then I will go into a little brief introduction to TSN for those who are just entering the event. And then I will talk about what is the problem we have with packet delay variation and how would we solve it. And then I will show some evaluations. Right, so Oliver just talked about this time-critical applications. Here I have two examples. So we have adaptive manufacturing cooperating AGVs, and they involve several AVGs and ARM processing cells, and safety critical zone where there are humans. So this requires a very precise coordination among AGVs and safety system. So this is a very critical service that needs to be precise and very well scheduled. Then we have exoskeleton in the industrial context, and here it's a person carrying an exoskeleton for helping them with their work. And in this case, we need an active exoskeleton, which means a lot of processing needs to be offloaded to the edge cloud, as you can see in the figure. And then here, this processing is real time, it needs to be done fast. And it has very low tolerance to jitter and delay, and it needs a tight scheduling. So these two words, coordination, scheduling, will lead me to what I want to develop in this presentation. Also from the 5G ACIA, we have this from a white paper, several traffic classes in the industrial automation field that are time critical and are not tolerant to jitter. Zero tolerance or very little tolerance to jitter. And so to handle all these cases, one technology that is central in this project and we have been talking about is TSN. which is a layer 2 technology, works with Ethernet. And it's designed to deliver deterministic services and that guarantee bounded, low latency, and very low packet losses. And then TSN is actually a set of standards of IEEE with a big tool set with several features. One of them is called scheduled traffic. We also call it QBB or TSN scheduling. And that's what I linked with the previous slides. So that's what we use with TSN in some of those critical applications. And another thing, we have also other tools, right, like time synchronization. There's many tools that I will not mention, but this is central for this presentation. And so in TSN, we have a talker and a listener, and there is a TSN stream that needs to reach the listener at the right time. It has to be the right packet, like it was said in the morning, at the right time, not before, not later. And to do so, we have this scheduling that is performed. So this CNC, which is a centralized network configuration controller in TSN, will make all the calculation based on the delay of the links and every single device in the path. And then normally it's not considering too much a large jitter. This TSN bridges has a very small packet delay variation or jitter. And so the schedule will tell the packets, the application, the flows when they have to be transmitted for the next step and so on. So it's a very precise scheduling. I will talk more later. So in 3GPP, we have standardized 5G system as a TSN bridge. And here, in the next slide, I show you a little bit of an introduction of the 5G as a TSN bridge. So it has been standardized in 3GPP. These wireless characteristics of the 5G system allows mobility, but it also is simple and easy to deploy. Of course, we have no wires. And then it's also giving some guarantees in the upper bound of the delay. And this is performed via the URLLC feature in 3GPP. But the characteristics of the 5G TSN black box that we painted before differ quite much compared to a wired TSN bridge. And this is differing by several orders of magnitude with respect to packet delay variation. But the 5G TSN bridge is very convenient. It has a very large coverage and covers a lot of distance. So basically, in this previous figure, you can make what we call a wireless bypass. So you don't need so many TSN bridges. So it has many benefits, but there is this problem. And we need to minimize or cancel this packet delay variation. And as you can see in the figure, it's very large. It's in the order of tens of milliseconds, while for TSN bridges, it's in the order of hundreds of nanoseconds. So it's a big difference. Now, in 3GPP, there was a concept proposed, which is the hold and forward buffering mechanism. And the idea of this hold and forward buffering mechanism was for the purpose of the jittering, which means we pace out the packets so that they are delivered at the right time before forwarding them. However, in the standardization, there were many discussions, many different views, and it was no agreement. And then the jittering functionality was not standardized. So this remains a problem and needs to be standardized for 6G if we want to achieve a low packet delay variation or zero packet delay variation. And indeed, it is there, but it's only specified to provide the basic functionality of QBB, which means you have the different traffic classes in your egress port, of the 5G, 6G system. And it will hold the packet if the gate for a particular traffic class is closed, and it will forward the packet when the gate for the traffic class is open, like the green one. So it's only showing this very basic functionality, but as you can see, it's not jittering anything. So this is something that we need. We need to cancel or minimize the packet delay variation. And one of the solutions is the packet delay correction. But let me show you what is the problem. What is the core of the problem? So we know QVV is managing the transmission gates, as you can see there in the top, the traffic classes, as I mentioned in the previous slide. And the transmissions repeat in QVV hypercycles. So every traffic class will transmit in a cycle, and then this same cycle will repeat, and so on. So that's the scheduling. And what happens is that the scheduler is thinking that these transmissions of different flows, stream 1, the purple, and stream 2, will arrive at a specific time. But what happens is that, for example, stream 1 should arrive, the packet should arrive before the yellow. But what happens if this jitter is too large? The stream 2 packet may arrive very quickly, while the other one may arrive very late. So then you switch the order. And this has very strong implications, because then you have an uncertain queuing and transmission order. This is a problem for those packets, but this is a very large problem, because this, if you can imagine, there's many more flows, and this problem propagates. There's many more packets that having queuing issues and will not be transmitted at their transmission window. This means that this packet will have to wait to the next hypercycle. So we are having now a big delay, and this is not acceptable. So this is the problem, and then we cannot guarantee the QoS, we're breaking the schedule. That's actually the core of the problem. And the reason is because of this very large packet delay variation of the 5G system between minimum and maximum in the figure. So solution is a packet delay correction. It's a very simple idea. So we have URLLC pushing down the upper bound of the delay, and then we have this packet delay correction pushing up. And the result is that the probability distribution remains very sharp, and that's what we want, because that means no jitter or very little jitter or packet delay variation. So how do we do this? Okay, we modify the packet delay at the egress point of the 6G system. And now I'm talking about 6G system because 5G doesn't have this feature. And then the idea is to reduce this PDV. So what do? We hold the packet until it reaches a desired target delay, which we have to choose carefully. And then we hold the packet and before forwarding it to the next node. Now, if you do that with all the packets in that flow, then all packets will have a PDV, will have the same delay, which means the PDV will be equal to 0. So if we can manage this, or to lower the PDV at least to the hundreds of nanoseconds, then we are in good shape. Another solution here is to design a wireless-friendly QVB scheduling. But that I will leave for my colleagues in the afternoon. Right, so I will present here one of the basic solutions, but in the project we have developed more solutions, more PDC mechanisms. So basically here you have the 6G TSN bridge. We have an ingress port, and there you add a timestamp to the packet. You insert it in the packet. And then at the egress port, you generate another timestamp. And then using these 2 timestamps, you calculate the real delay that the packet has experienced in the system. And then you hold the packet in the hold and forward buffer for that difference with the target delay. So you want the packet to experience a specific target delay. So you let it wait until it's time. So in this way, we achieve to bring down to 0 or very small PDV. And here we have some simulations that, as it was mentioned, they were based on the extensions done to Omnet++. In this scenario, we have an automated guided vehicle network, which is connected through the TSN backbone and a logical 6G TSN bridge to the factory, the network of the factory there in the right side. And this setup, well, as it was mentioned, this is using the 6G.com simulator extension. And it uses, this extension uses real measurements of 5G delay histograms. And the design is to have 90 frames per hypercycle with delay of 20 milliseconds and 50 wireline streams, which means they stay in the wireline network. And we have 40 wireless streams, which means they traverse the 6G TSN bridge. Here references to the deliverable. Right, so this is the first result. It's an end-to-end latency probability distribution in the shape of violin plots. And here, so we have end-to-end latency in milliseconds. And there we have the different options. The first one was best effort. We are not using PDC and we're not using QBB. So basically, in this case, you're having a distribution that is equal to the, almost equal to the 6G delay distribution. So even when it's below the deadline, it's still not good because we don't want the packet to arrive before or later. We need the packet to arrive at the right time. And we cannot tolerate jitter. So this has a lot of jitter. The second one, then we have QBB without PDC. This is the problem. So as you can see in the middle, the yellow, so we have a group of packets that arrive on time, the right deadline. But there is another group there on the top, obviously above the deadline. So in that case, what happened is what I explained before. There is an wrong queuing, and packets are missing their chance to transmit in the current QBB hypercycle. They need to wait for the next one. That's why you have like a double waiting time there. So they need to wait the whole cycle. And then when you apply QBB with PDC, then it's absolutely flat, deterministic, because you are forcing all the packets to spend the same delay in the 6G system. So it's absolutely dependable. So it's a solution that could be used. In the next one, we have more like what is the relative arrival time over the simulation time. And then every color is a different flow. For it to be correct, you should see a straight line, single color, because that means consistently every cycle the packets are arriving at the right time. But here what do you see with this close-up is that packets of different flows are being transmitted when they should not. Why? Because they are taking their place. Because there was a wrong enqueuing and the transmission order is also wrong. So then those packets are being held and transmitted. So then you have several flows that are above the deadline. So this is absolutely not okay. In the next slide, then we have with QBB, with PDC, and then you see that absolutely there's no interference. Packets are transmitted at the right time, and there's no queuing ordering issues. I now reach to my conclusion, 5 minutes ahead to compensate. So, packet delay variation of a wireless TSN stream is larger by orders of magnitude compared to a regular TSN bridge. And these large PDBs makes this TSN scheduling QVB more challenging or very difficult to apply. And this can lead to unrobust behavior and uncertain in queuing and transmission orders. So that's what we have seen in this presentation. So the approaches to overcome this are using a packet delay correction, which is a simple way, simply enabling any QVB TSN scheduler to be applied. Any available, there are many today, so it's a good option. You can use any of the available algorithms. And then, however, it trades PDV for a larger average latency, since you make the packets wait in the hold and forward buffer. The other solution is the wireless-friendly QVB scheduling, which is going to be presented later today. And with this is the end of my presentation. Thank you so much, and I welcome your questions.
Thanks, Marilyn. Any questions? Yeah.
Thanks, Marlet. Can you go back to the where you were presenting the next? Here. So here in the best effort, we see that okay, we don't have QVB, we don't have PDC in the best effort. The packets arrive and they still meet the deadline, right? Do you see worth? Adding the, I know it's a bit contradicting, but adding the packet delay compensation if by having a sort of over-dimensioning system where you have like a very low delay, even some packets get into the next hypercycle, they can still meet the deadline for the scheduling. Is that worth all this, adding this sort of compensation and all that stuff?
I'm not sure I understand. You mean if you have an over-dimension system,
yeah,
where the delays here are...
Yes. Even they
will always arrive early.
Yes.
Yes. Well, if you can guarantee that. The thing is, that could be a possibility. Always, if you over-dimension, then you can safely deliver early. All the packets will arrive early. But it depends also in interference and other aspects of the radio channel. Mm-hmm. And you cannot guarantee 100% if the traffic grows. Mm-hmm. But yeah, if you over-dimension, then you kind of could solve this. Okay.
Just playing the die.
And I wanted to say that you don't always need QVB. You can also, if you don't use TSN, you can also apply PDC when the application is not tolerant to jitter, even if I didn't mention it before.
Okay,
yeah.
Thanks.
Thank you.
Here on the online, but maybe I want to comment on this. I mean, over-dimensioning solves, capacity limitations, but of course, the latency variation comes from the wireless characteristics independent of load. I don't think you can get rid of the jitter over the wireless channel. So this is by an orthogonal kind of dimension. But then I would read now a question that we got online, and this is, given that 3GPP does not mandate TSN support in the G-Node B, how is jitter managed within the G-Node B, particularly in the case of a disaggregated G-Node B? Is the PDC, so this packet delay correction function, also implemented at the G-Node B?
No. We have not implemented anything in the G-Node B. What we have done in the project is some run scheduling. but mainly for the purpose of minimizing the delay and aligning with the application's timing. So that's things we can do, but we haven't applied this to. However, we have PDCs that I haven't explained here that are only applied in the run section, the run segment between UE and GNodeB. So if this is possible, then, but it still needs a standardization. Mm-hmm. Yes?
So if understood right, this, time stamping will be applied in the network TT and the DSTT, similar to how it's done now for the time synchronization. And then, how those modules will get the information about the specific flows. Is that the CNC, the one that needs to communicate what is the expected delay for some of those flows in order to apply a specific compensation?
I think this figure is incomplete. There is a CUC, which is another controller, and that one communicates with the application to get the requirements. It gets a lot of information from the applications, and what are the deadlines and the requirements for the flow. And then based on that, this information is passed down to the CNC, and the CNC makes all the calculations on the scheduling based on that input information. Now also the bridges, even the 5G, sends what is the bridge delay. They send it to the CNC. So CNC has all the information and makes the scheduling calculation.
Right.
Is that the answer to the question?
Yeah. So basically the CUC needs to figure out what is the flow ID for certain application. Then depending that, okay, this flow should have a total delay of X milliseconds, then needs to distribute that and say that to the 5G or 6G system that this flow, you need to compensate that the total should be this amount. So then there's a granularity per flow and packet delay compensation, right?
It's more the other way around. The 5G system would tell what is my bridge delay, and you guarantee that. But what we're doing here is not only guaranteeing the delay, but also compensate for the delay. So all packets have that latency, and we have no jitter. So the CNC doesn't tell this 5G system or the 6G system what to compensate or how to compensate. It only, the bridge tells the CNC, this is my bridge delay.
All right, okay.
Now, in the 5G system, it is very large jitter. So what we need to do is tell what is the bridge jitter and then the bridge delay, and then push up all the delays of all the packets to a single value. Then we will have 0 PD.
Right, so there is no delay compensation per flow, just per system for the whole system.
It is per flow. I haven't gone into the details, but every flow has their own requirements. So you could specify it per flow, or you could specify it per port, per traffic class, per traffic class and per port pair.
Right, okay.
Yeah.
Thank you.
Thank you. Interesting discussion, but we need to move forward. So thank you very much, Marilette, for your very nice presentation.
Thank you.
Okay, and the next topic will be this machine learning techniques for KPI prediction by Sami.
Nice. Hello, everyone. I'm Sami. I am now employed at Ericsson, but some of the contributions in the context of deterministic 6G that I was involved in regarding KPI prediction or latency prediction activities was during the time that I was at KTH. So consider this as sort of a joint contribution. we were involved with different people in this project, and so this would be the presentation of those contributions in, I think, mainly work package 2, if I'm not mistaken. But let's begin with thinking about why we need KPI prediction. When we look back in the legacy mobile era, we think of 2G, 4G, and like early 2000s, and the main basically service that these mobile devices were targeted to address were like voice conversations focused, and interactive web browsing, voice conversation, and in these cases we had like latency targets of 150 milliseconds and like reliability of like 99%. If that was satisfied, you could have like a nice voice conversation, right? And similar to that for interactive web browsing, and it worked fine. And then in 2010s, during those years, the idea of tactile internet was introduced, where we have like all devices like connected to mobile networks, AR devices, AR headset, VR headsets, robots being controlled, drones, and so on. And the major difference here is that those latency targets or KPI targets won't work here, right? Motion to photon latency in terms of like human in the loop applications, they have the target of like 5 to 20 millisecond and like 3.9 reliabilities, meaning packets or frames that are being pushed to the device, 1 in 1,000 can have a larger delay than, for example, 5 millisecond, which is compared to what these systems were previously designed is a major shift, right? And when it comes to cyber physical systems or robots and drones that are connected, as we all know, these latencies should be pushed to lower bounds, like 1 to 10 millisecond and like 5 nines reliability. And what will happen is already covered in the previous talks, right? And on the side, we should think of the data rates as well. Like in XR use cases, we have high data rate demands as well, like 25 megabit per second, 400 megabit per second. If we are pushing like 4K streams to the device, which is very bandwidth hungry, in cyber physical systems, it's on the lower end, but still if there are visual feedback or visual transfer, that needs also high bandwidth. So then 5G came, and there was this like different ideas trying to address the needs of this tactile internet. And the main one that everyone's talking about, URLLC, which was supposed to turn the radio link into a wire, sort of, and give us like less than 1 millisecond latency and very high reliability levels. And there were certain features that were introduced as standardized, but in practice, the idea is that it kind of fell short due to basically silicon cost, complexity of RF implementations, economy of scale wouldn't allow like these devices to be implemented. And those 6 nines were like still on paper could be achieved, but in reality, still it was not proven that they can satisfy that. And we had on the other end, quality of service and network slicing for isolation of resources. For example, you have premium users, you want to have quality of service for those premium users satisfied, you do isolation from the best effort traffic for them. And on the other end, the adoption was slow on this end as well, due to many reasons, one of them being scalability limits. If I have 10 quality of service, high quality of service users, can I accept like 10 more, considering the current load on this cell, for example? These were like questions that slowed down basically the adoption of these technologies in 5G. And out of many other ways that in this area is being proposed for 6G or like even in 5G advanced complementary approaches, one of them is to use AI or machine learning or data-driven techniques to predict the KPIs and adapt around that. So if I can predict what's going to be the capacity of the link or the throughput for these 10 users in this cell, considering that I have like hundreds of best effort users, then I can maybe decide whether or not I have to admit another one or more, or what to do to keep the SLA satisfied for these users, right? Because these systems are complex and they are dealing with lots of stochastic elements in them. So why not build some approach to learn this stochasticity based on the context that they are deployed on, right? So this is one of the approaches that could complement this set of approaches that were already introduced. And when we want to think about KPI prediction with machine learning tools, first question is, okay, what we want to predict, what we want to train a model to give us an insight, to produce us an insight that can be used for next 10 minutes or next second or 10 or 100 milliseconds. But the question is it really predictable? Right? That's the first question that one can ask to make the prediction algorithm, choose the right prediction algorithm, and define the right problem. And that's very important that we also have a contribution around that was discussed in the morning as well. How do we define predictability for these network KPIs? Based on randomness of the network, based on the observability that we have, and maybe in the future we can look at based on which conditions of the system that we can collect data, right? So this is a very important aspect. But what we want to focus now here is, okay, when we want to build these prediction models, what is it that we need to be careful about, and what are the important aspects of that? And we will dive into three aspects. First, probabilistic prediction is important, and before the project or in the early phases of project, we were seeing very few works in the research area, in the academic society on these probabilistic prediction aspect. And that kind of comes from predictability question, I think. So the KPIs that you see from the network, they have these random variations and stochasticness. If you train a model to give you the value of delay, let's say, or 1 point estimate for the throughput, is that really the right way of formulating the problem? Because you always have an error, because we know there is a stochastic variation, right? So why don't we define the problem in the right way and ask if we can come up with an answer that already includes the uncertainty in it. So we do probabilistic prediction. Second is that where URLC lives, those 6 nines, 5 nines, 4 nines, we want an accurate prediction for that region as well, and that was something we found very underexplored and needed specific approaches and methods in machine learning. And the third aspect is these systems expose temporal correlations when it comes to latency, when it comes to throughput, and especially when we are looking at queue states and so on, what you observe from the system can have an implication for the KPI in the next 100 milliseconds or 1 second maybe. Right now, for example, the signal quality is low, the UE is moving towards like the edge of the cell. Maybe in 1 or 2 seconds we can have a chance of handover, right? So can we design or use the ML models to predict these aspects? Let's focus on probabilistic prediction and have a dive in the approaches. The figure here is packet delay, as I mentioned, measured from a live 5G link. And what you see is lots of variations, right? And we have this dashed line on 200 milliseconds, which let's say that's the requirement of the application. Let's say that's the SLA requirement. And 200 milliseconds is big, yes. let's say it's voice conversation. And on the other hand, it always comes with this probabilistic measure, reliability measure. Like we want 200 millisecond with like 99% of the time, right? And we turn this plot into the CCDF plot, which shows us with which probability we get a violation of latency for a specific target. On x-axis, we have the target delay, and on y-axis, we have probability of violation. And that red dashed line turns into the vertical dashed line in the bottom figure. And what we ask, and what does SLO mean in this context, service level objective, is the combination of this deadline, let's say, with the reliability factor. And as we know, and this is what I call the tail probability, this violation probability, that in URLC word, the areas around 10 to the power minus 5, minus 4 is really important. Because those are 6 nines and 5 nines corresponding to those regions. And the ML problem that we suggested to define is to say we want to estimate the probability of having a certain KPI, let's say throughput or latency, given the conditions of the network, state of the network, the load, quality of the link, and everything you can think of. And on the other hand, we want to collect a data set, right? What do you, in supervised learning, you typically need the value that you want to predict in your data set as the label, and you have certain features. You collect the samples, feed it for training, and it works. But here, we are doing probabilistic prediction that we collect the same data set. So we collect the KPI measurement together with the conditions of the network, and the algorithm, the negative log likelihood loss in the context of mixture density network takes care of the training for you. And the output of the model would be probabilistic, basically. There are other ML approaches like Bayesian neural networks and others. Like in gradient boosting, also there are approaches on like probabilistic prediction, and that's very interesting because more people are working on that on them. And but our implementation was based on mixture density networks. And as I mentioned, there must be extra care when it comes to the tail. And that region, training a model for the tail, -5, -6 probabilities, needs a lot of samples. The measurements in this figure we took from a private 5G system in our testbed at KTH. And we trained this mixture density networks model on two approaches. One conventional approach, GMM, which you have Gaussian mixture, a mixture of Gaussian distributions that is the output of the model. And EVM is the one that we append or we stitch a Pareto distribution to this mixture. And Pareto distribution is very efficient, and in cases where we have low number of samples and we want to look at those heavy tail distributions, or at least 10 to the power -4, -5. And 4 million samples, the blue curve is where we collected 4 million samples of latency for packets. And the rest in the plot you see are basically trained models with different number of samples, and the EVM is clearly outperforming the conventional approach. But and in the next question or next problem that one can define is this aspect of sequential prediction. We have not one network condition, but we have a history of network conditions. Let's say our model can look at a sequence of condition vectors. So what we can observe from these networks right now, like in terms of observability, it's very strong. We can collect from different points of the system different information. And I would say feature engineering in these prediction approaches is very important. What do I pick as the data to include in my condition vector is very important, and that affects the accuracy of the model. But having said that, we need a certain model. We need to train a model to take us from this history of condition vectors to what's going to happen in the future. And again, we designed a probabilistic approach as well, where we use transformers and LSTMs for this approach. Because this is a typical time series prediction in machine learning. And these models, transformers and LSTMs, they are able to pick up patterns. They are able to understand trends in the data and extrapolate that for the future. So if you have dependencies, temporal dependencies, in the way that your system works, these models are proper models to throw at the data. And we ran these on the 5G network at KTH. So we collected data from internal signals of the RAN, for example, MCS index, channel quality measures, retransmission counters, buffer status, and all. And those, like we defined a certain context vector or condition vector, and then we trained transformers and LSTMs, and also on the other end we measured latency, the latency that happens corresponding to these conditions, and that's a time series or sequence, and you have condition sequence. So we trained the models, and interesting observations we had. Here on the left-hand side, you see a conventional prediction. Blue line is the latency of the link, and these are like in the very small scale. This is like maybe you are looking at 100 milliseconds or 500 milliseconds here, half a second. So we have this correlation of latency, like this sawtooth that happens due to synchronization aspects. And then you see there are certain random, basically, jumps. Those are coming from the retransmissions. And what we are doing at time step 0, we are for the next 100 time steps, we are asking for the distribution of delay. And you see different shades. These correspond to different quantiles. So it means your latency would, for example, would violate 26 millisecond or 24 millisecond with different probabilities, right? We are predicting a distribution, and that's why there are different shades. But the left-hand side, which is the simple MLP prediction, it's constant for the next 100 time steps. It doesn't understand the notion of temporal correlation. But on the right-hand side is when we apply LSTMs or transformers. And they can see in the future the trend or the pattern of the KPI, because they are trained and they know how this basically dependency is going to turn out in the future. So it goes down, so the distributions go down until from 0 to 75, and then they go up and go down. So, and they are still capable of covering those stochastic retransmissions as well. You see those different shades, some darker and some lighter. And transformers in our benchmarks showed the best performance. So they needed, compared to other approaches like LSTMs, they needed much less samples to pick up these trends and to pick up these temporal correlations. And they could predict further into the future with less number of samples. So they show great, and they show very promising results to be deployed in real scenarios. Because when it comes to real deployments, it's very important to understand these limits and understand how much of these conditions we can incorporate in our data set and how much data we can store for each condition scenario. Going for the conclusions, what we started was based on the fact that we want to have a prediction. We just don't want to provision these features to make promises, but also we want to be able to predict, understand what's happening, and maybe adapt based on the prediction and the understanding around the KPI. And it is very important to define the right ML problem. And in our case, we think probabilistic prediction is the way to go because all the all the understandings of the system that already described. And what we can use these systems for are, for example, for the planning phase. If you don't think of LSTMs and transformers where they are more suited for live interactions with the system, you can train your models only for planning phase and say, this location with this environment gives us like with 4 nines we can support 100 millisecond, but the other location which is central in the, for example, in the city, and there is lots of interference sources, for that I cannot satisfy 100 millisecond, maybe 500 millisecond with 3 nines, right? So this can be used for planning. And also the second, like the sequential models, maybe they are more suited for proactive RAN operations. If I know in the future this is going to be the delay, maybe I can come up with increase the resources basically, or reduce the MCS index, or do something to compensate that. And what if analytics also are important, and I think they go hand in hand with the planning at mission control. What if another user joins? Then these models can for sure be beneficial in answering these questions. And next steps, and in my opinion, what's very important to focus on to actually deploy these models and use them in 6G maybe, is about how to define a proper data collection campaign, or how to define the problem based on our capabilities that we have for data collection. Can we collect data from live networks, or can we collect data from test beds? And if we train models, can we then use them in real scenarios, so that the transfer learning aspect is also important? Or you define like an online learning problem or incremental learning. So we train a model in-house and then we incrementally update it when it's deployed. So these are the open questions that one can answer in this domain. Thank you for listening. I'd be happy to answer if there is any questions.
Thanks, Sami, for the very insightful presentation. So I actually have 2 questions. So the first one is going back to Prof. James' presentation before, in which he said that if we can predict the KPIs for some time in the future, then we don't need to have a single operation mode. We can adapt the operation mode over time.
Yeah.
So my first question is that in your prediction, if you can predict that in the next, for example, 100 milliseconds, that the delay will be violated. I mean, the delay requirements will be violated. So you ask for 99%, but it can only satisfy 95%. Then what would you do? What would be the action, that concrete actions that you do? And my second question is that in the beginning of the presentation, you state a certain reasons for why your LLC and network slicing has not been successful so far. Then you propose the solution of using KPI predictions, but unfortunately, I'm still not really understand how can that KPI prediction can solve the original problem. Thank you.
For your first question, I think there are many ways that predictions can be used, as we mentioned, right? First is, I think your question was more towards like, if we know something is going to happen, degradation in latency or KPI, how can we compensate that? And for that, it's either we decide to like compensate it in a closed loop. So there is discussions of like using these ML models in closed loop, right? So you get an insight, and based on that, you decide to optimize the RAN functionality. That's one way. And the other way is to maybe these insights would be used by the application side. So if the robot is moving to a poorly covered location, maybe it should reroute, right? There is still there are many ways that the models can be used, but for sure, I think it would be a useful insight to produce and make a decision based on that. And for your second question, I think, so what I mentioned is, so yeah, there was many reasons that your LLC didn't fly. And one of them, or like in combination with quality of service schemes, one of them was the scalability aspects. And basically there was not much insight on, okay, how many of these SLA streams I can afford in my system based on the context, right? And how much, for example, the monetization aspects were also unclear. So these are, and like there are many solutions people are working on. One of them is KPI prediction or ML algorithms that can help in some way or the other to this scheme. So it's not a full solution at all, but just one tiny thread that people are following, hopefully to improve the situation there. But the connection with your LLC was mainly, so your LLC and like 5 nines and 6 nines where we are thinking of, those regions in reliability, they are basically very difficult to model and come up with an prediction based on, for example, simulations or based on channel models, let's say, on the RAN and knowing, okay, the probabilities of retransmissions are this much. These regions, like 5 nines, 6 nines, they should be characterized in a data-driven manner. And that means run the stream of packets forever on this link, and let's see in a day how many times I would violate like 100 milliseconds, right? And the data-driven approach takes us to we want to have efficient data-driven approaches, and frontier of them like ML approaches are basically a candidate. So that was the connection to your LLC that makes these approaches be promising, at least. Yep.
Okay, last question, I guess. But
so your, let's say, measurement and control is outside the G node B loop, and in G node B you have a schedule that is doing reshuffling of the packages and resending, so its own optimization. So adding one additional loop on top of the one loop, would that cause confusion or self-oscillation issue? So you are compensating something that is already compensated, then they will adapt to your compensation, and then it's kind of a...
Yeah, that's true. For proactive RAN operations, I fully agree with you. It has to be the domains that each loop is taking care of. If there is proper isolation, like if they are not, if we are not optimizing the same parameter, this has to be taken care of somehow. But in planning phase and admission control, that there is room for these algorithms to play a role, I think. Yeah.
okay, so thanks again, Sami. And I think this is the time to conclude the morning session. So thanks for all the presenters in the morning. And for the online audience, we will have a longer break right now, and we will continue with 1:30. And for the on-site participants, we will have the lunch break. Now, I guess we should start with a short 5 minutes bio break, and then we can walk to the canteen together. The door will be locked, so you can leave everything. Yes, you can leave everything here, and that's it. So 5 minutes short break, and then we will have a short walk. The restaurant is in this building, so we will not go outside.